Thank you for your introduction. So I'm Takahiro Ueda, a postdoc at Center for Astrophysics. So today I'm going to talk about the evolution of solids in gravitationally unstable protoplanetary disks. So Oha-san said that I will talk about how planets form. But in this talk, I'd like to talk about the planet cannot form in this disk. Okay. And this work is already published in the Nature Astronomy last year. So if you are interested in, please check it out. And okay. So I'm going to talk about the evolution of solid materials in protoplanetary disks. And this is a central topic of the planet formation. So if you are not familiar with the planet formation, so please feel free to interrupt anytime. And okay, so in the protoplanetary disk, dust particles are expected to be very small with size of the micron size in the earliest phase of the disk evolution. But they collide each other and grow larger by collisional sticking. And if these particles grow to the size of the millimeter or centimeter, these particles are so-called as pebbles. And these pebbles can grow to the planetesimals by some hydrodynamical instabilities or the collisional sticking. And eventually planets are formed from the planetesimals. So the planet formation is a very long journey of solid materials in disks, ranging from the micron size, which is a 10 to the minus 5 millimeter, 10 to the minus 5 meter, to the 1,000 kilometer, which is a 10 to 6 meter. So the size range is roughly the 10 orders. So this is a schematic picture of the protoplanetary disk. And the right side of this figure shows the dynamics of the dust in disks. And the left side shows the schematic picture of the disk observation at each mid-infrared wavelengths, near-infrared wavelengths, and millimeter wavelengths. And at the earliest phase of the disk evolution, where the dust particles are very small, then these small particles are well mixed with gas. So the dust particles are uniformly distributed in the disk. But if they grow larger, these large particles start to sediment to the disk midplane due to the gravity from the central star. And if these particles can grow larger to sufficient size, let's say millimeter size or centimeter size, they start to drift inward to the central star. And sometimes they collide each other with very high velocity, and such high velocity collision result in the violent fragmentation. And if we look at these disks at near-infrared wavelengths, then these infrared wavelengths traces the disk surface, which is characterized by the distribution of small grains. But if we look at this disk with millimeter or centimeter wavelengths, then we can observe the disk midplane where the large grain exists. And in the disk, there is some barrier in the dust evolution. The one barrier is so-called radial drift barrier. So in the disk, dust particles rotate around the central star with a Keplerian velocity, because the gravity from the central star should be balanced with the centrifugal force. But if we look at the gas disk, there is a pressure gradient force, then the gas disk rotates slightly slower than the Keplerian velocity. So there is a difference between the rotational velocity in the gas and dust. And eventually, the dust particles in disks feel a headwind from the disk gas, and losing their angular momentum and spiraling to the inner region of the disks. And the right figure shows the radial drift velocity as a function of the Stokes number. And the Stokes number is a dimensionless stopping time of dust particles. So if you are not familiar with the Stokes number, please just remember that this Stokes number is roughly proportional to the dust size. And you can see that if the Stokes number is unity, then the radial drift velocity is the maximized. Okay? So, and this Stokes number of unity corresponds to the dust radius of roughly millimeter or centimeter size. That is why we called this dust size with this size range called pebbles, which is different, hydrodynamically different from the small grains, right? And you can see that if the dust size are order of millimeter or centimeter, then the drift velocity is roughly two orders of magnitude higher compared to the small grains. So the dust size in disk is very, very important to understand the dust evolution. And if we look at the real protoplanetary disk, this is a very beautiful gallery of the class 2 disks, which is a kind of older disk population with a typical age of the 1 million year or older. And you can see that the multiple ring and gap-like structure in these disks. So these substructures are expected to be formed by the dust radial drift, because if these radial drift of dust particle can be halted at the pressure maxima, where there is no difference in the rotational velocity of gas and dust. And at such point, dust particle can accumulate. So there is this kind of the local dust concentration can be seen. So if this kind of substructure is achieved, then local dust density can be increased by orders of magnitude, and eventually planetesimal can form by some streaming instability or gravitational instability in these disks, these rings. However, there is another barrier in the dust evolution, which is called as the fragmentation barrier. So this is a numerical simulation of the collision of dust aggregate in protoplanetary disks. And in protoplanetary disk, typical collisional velocity is expected to be the order of the 10 to 100 meter per second. But based on these simulations, the fragmentation velocity above which the dust collision results in the violent fragmentation is expected to be the order of 1 meter per second or 10 meter per second. So that means that the typical collisional velocity is much higher than the fragmentation velocity, meaning that the dust particle cannot grow larger at some point because of the fragmentation. And if we compare these velocities, we can roughly estimate the maximum dust size in disks with this equation. And the key point is that this dust size, A frag, is inversely proportional to the turbulence strength, and also the proportional to the square of the fragmentation velocity. And maybe, as you know, the turbulence strength and the fragmentation velocity, both these two parameters are very, very uncertain in real disks, which means that the maximum dust size in real disks is very also uncertain, right? So the central question in this talk is that how much is the actual dust size in disks? Or more specifically, how much are the turbulence strength and fragmentation velocity in these disks? So this is a central question in this talk. And in this talk, I'd like to focus on the protoplanetary disk around IM Lup. And the reason is that the protoplanetary disks are expected to be gravitationally unstable at earliest phase of the disk evolution. So this, the gravitationally unstable disk is expected to set the initial condition of the planet formation, right? And this IM Lup disk shows the very beautiful spiral structure as shown in this figure. So this disk is very, very bright and popular. So there are a lot of observations, such as the ALMA millimeter dust continuum observation, and the millimeter polarization, and also the near-infrared polarized scattered light observation. So there is a very, very beautiful observational images of this target. So in this talk, in this work, we construct a theoretical model to explain all of these observations in a very simple, unified picture of the protoplanetary disk. And before going into the details, I'd like to briefly mention about the what kind of quantity each observation traces. So if we look at the millimeter dust continuum observation, these observations basically traces the large dust particle exist in the disk midplane. And this millimeter dust continuum is basically observing the dust thermal emission, so that this intensity of the millimeter dust continuum is basically depends on the dust temperature and optical depth. And the optical depth is basically the product of the surface density and the opacity. So this millimeter dust continuum observation is sensitive to these quantities. And the millimeter polarization is basically very similar to the dust continuum, I mean the Stokes dust continuum. But this observation is more sensitive to the scattering albedo of the dust particle. So this is because in the protoplanetary disk, the dust thermal emission from the inclined protoplanetary disk can be polarized in the direction parallel to the disk minor axis due to the scattering. So this is one of the most beautiful images of the scattering polarization from the HL tau disk. And you can see that the polarization vector is parallel to the disk minor axis, right? And this kind of pattern can be explained as follows. So this is a schematic of the inclined disk, and this is a line of sight. So we are observing from this direction, and we are observing the intensity from this point from this direction, and this you can imagine that the emission from this point is coming from this region and eventually scattered by this scattered to this direction. And if we focus on the emission from this direction, you can imagine that the electric vector oscillate to this direction cannot come to this direction, because only the vector perpendicular to this line of sight can be scattered to this direction. And this electric vector is vanished when the light is scattered to this direction. But from this direction, you can imagine that this vector can scatter to this direction. But this one can still scatter to this direction with some portion because of the effect of inclination. And eventually, the electric vector oscillates in this direction. It's a bit stronger compared to this direction. Because of this combination, we can frequently observe this kind of the polarization pattern parallel to the disk minor axis from the protoplanetary disk. So this is a very common phenomenon if we observe the disk with polarization. And the important thing is that this scattering polarization efficiency is very sensitive to the dust size. And if dust particle is completely compact, you can imagine the very spherical compact dust aggregate. This figure shows the polarization efficiency at 1.3 millimeter, which is the ALMA band 6, as a function of the maximum grain size. This polarization efficiency has a very strong peak at the size of roughly 0.1 millimeter, which corresponds to the observing wavelengths divided by 2 pi. So this means that if we observe this kind of scattering polarization, we can estimate that the maximum dust size should be this regime, right? If dust is compact. But actually, this scattering polarization efficiency depends on the dust porosity. And if the dust is moderately porous, this black solid line, black dashed line, this polarization efficiency has a much broader peak, meaning that the scattering polarization can be induced with very large dust size range. But if dust is too highly porous, this polarization efficiency decreases, so there is no detectable polarization. So based on this kind of argument, we can estimate the dust size from the scattering polarization. And finally, if we look at the disk with near-infrared wavelengths, this observation basically traces the distribution of small grains well mixed to the disk gas, meaning that this distribution is basically determined by the gas scale height in the disk. So if we look at this one, millimeter dust continuum of the IM loop and the near-infrared polarization image of the IM loop, these observation traces very different dust population. Okay. And before going to the details, this is very schematic summary of our model. And we found that this disk is divided into 3 regions. At the very inner region, within 20 AU, the disk is heated by the viscous accretion. This viscous accretion increases the mid-plane temperature very efficiently, so that the millimeter emission is also bright. And this mid-plane heating increases the gas scale height, and the disk is vertically puffed up at the very inner region. And because of this geometric effect, stellar irradiation onto the outer region is blocked off, right? And there is a very huge shadow extending out to the 100 AU, and in this shadowed region, there is no stellar irradiation onto the disk surface. And in this region, eventually the disk temperature is determined by the external heating from the interstellar medium. And at the very outer region, beyond 100 AU, the disk is starts to flare up. And again, the disk surface can receive the stellar irradiation at this point. And because of these geometry, based on this geometry, we found that the dust particles should be very, very fragile with a fragmentation velocity less than 1 meter per second, meaning that the radial dust drift is very inefficient in these disks. And there are a lot of small grains vertically mixed up, and generation of the small grains from the fragmentation also enhances the accretion heating at the inner region. And also we found that the dust particle should be moderately porous to explain the observed millimeter polarization. So this is a summary of my talk. So if you are not familiar with this topic, so please just remember this figure. So that's enough. And from now on, I'd like to talk about my model in detail. Okay, so my model, my work is divided into 4 parts, and the first step is an analytical model of the gravitationally self-regulated disks. In this model, we assume that the disk is gravitationally self-regulated, so that the tumulus Q parameter is roughly the unity at everywhere in the disk. And based on this assumption, only one key important parameter is disk temperature. So we introduced the accretion heating and the external heating, and also effect of the shadowing. I will explain in detail later. And based on this analytical model, we performed the evolution of the dust in disks. We performed the dust evolution simulation in disks. And we calculate the evolution of the dust size distribution at each radial point, considering the dust coagulation, fragmentation, and the radial drift, and the turbulent diffusion. And in this simulation, we vary the fragmentation velocity as a free parameter to investigate the effect of this parameter onto the result. And based on the dust distribution obtained from this simulation, we performed the radiative transfer simulation by changing the dust opacity models. And we obtained the images at the millimeter and the near infrared wavelengths. And also we obtained the temperature structure of the disk and compare it with the observations to verify our model. Okay, and so our model is very simple. The concept is that the disk structure is regulated such that the tumulus Q parameter is critical value, which is typically the 1 or 2. In this work, we assume that the 1.4, just for simplicity. And this assumption can be understood as follows. If disk is gravitationally unstable, meaning that the tumulus Q parameter is less than unity, then gravitational instability is triggered, and the turbulence strength alpha increases. And this increase in the turbulence strength of alpha reduces the gas surface density, and eventually the tumulus Q parameter is higher than unity. And if the tumulus Q parameter is higher than unity, then gravitational instability is deactivated. So the alpha value will decrease. Then again, the surface density increases and the tumulus Q parameter becomes lower than unity. So based on this argument, we can imagine that the tumulus Q parameter should be equal to the critical value of 1.4 in this disk.
But in this case, there is no mass coming into the disk anymore, right?
Yes, we assume that.
Whenever you have a higher alpha, then mass of the disk just go to the star.
Yes.
Then this mass gets decreased.
Yes.
Then how alpha can again increase?
That's a good point. So in the typical class 0 or class 1 disk, there is a mass supply from the envelope. So this kind of the argument can be speculated, right? Yeah, that's a good point. Okay. This disk, actually there is no envelope component around the disk. So this disk is isolated. So I'm not sure this assumption can be valid for this disk. But just we are observing the spiral structure. So simply we assume this disk should be some equilibrium in the marginally gravitationally unstable. And this assumption and the tumulus Q value can be written as this equation. And based on this equation, we can obtain the gas surface density with this form, right? And we know the tumulus Q parameter is equal to the 1.4. And we know, so the only free parameter is sound speed and the Keplerian velocity, right? A Keplerian frequency. And there is an additional assumption, which is the mass accretion rate is constant across the disk. And based on this assumption, we can also, and the mass accretion rate can be written as this form, the 3 pi gas surface density times the viscosity. And based on this assumption, the turbulence strength alpha can be also written as this form. And now again, we know the critical tumulus Q parameter, and the free parameter is the sound speed and the mass accretion rate, right? And key point is that for this object, we know the mass of the central star and the accretion rate onto the central star based on the observation. So only the free parameter is the sound speed in this model. The other parameter is completely limited by observation, okay? So that is a very good important point. So only free parameter is the temperature. So the temperature is very important to construct this model. And this figure shows the mid-plane temperature as a function of the radial distance. And this blue solid line shows the typical temperature profile obtained from the assumption that the temperature is determined by the irradiation from the central star. Okay? And this is a very commonly used temperature model where the temperature profile is temperature is inversely proportional to the R minus 0.5. Okay? And the key point is that if we look at the brightness temperature of dust particle obtained from the very high resolution ALMA observation, you can see that outer region, the brightness temperature is lower than the temperature expected from the stellar radiation. It's totally fine, right? If the disk is optically thin, then brightness temperature should be lower than the physical dust temperature. So it's fine. But if we look at the inner region within, let's say, 10 AU, this brightness temperature is higher than the typical temperature estimated from the stellar irradiation. So there is some missing heating component within 10 AU, right? And because of the beam dilution, the brightness temperature has a plateau in this location. But this is simply the beam dilution effect. So the key point is that there is a missing heating source in this region. So we propose that the real temperature should be like this. So this is just our model. But the point is that at outer region, the temperature is determined by the external heating, and the temperature is roughly the 15 Kelvin, something like that. At the inner region, there is a viscous heating. And this viscous heating has a power law index of the minus 9/7, which is very steep. So this is and this temperature structure can be inferred from the gravitationally unstable disk model. And this is just an assumption in our model to explain this increase in the brightness temperature in the ALMA high resolution observation. And if we obtain this temperature structure, then we can estimate the gas surface density and the turbulence strength alpha, like this equation. So this is very simple model. I don't want to explain details, but for example, if we look at the turbulence strength alpha, this value is something like 10 to minus 3 at the outer region, but it steeply drops to the inner region. And the gas surface density, it's very high, roughly the 10 to minus 4 at the 3.3 AU, and it's 10 gram per square centimeter at the 100 AU, something like that. Anyway, if we know that temperature structure, we can obtain the surface density and accretion stress based on the observational value, right? And based on this gas disk structure, we performed the dust evolution simulation shown in this movie. And this movie shows the dust size distribution and the integrated surface density in the bottom. And the left panel shows the simulation with the fragmentation velocity of 0.3. So which means that the dust is very, very fragile. They cannot grow larger at some point. And in the right panels, I assume the fragmentation velocity of 10 meters per second. So dust is very sticky and they grow larger. And you can see that they grow so for example, in the left panel, the dust size is regulated by fragmentation. And this magenta line shows the maximum dust size regulated by the fragmentation. And you can see that in the very fragile dust model, the dust surface density is almost doesn't change with time because dust is very fragile, very small. So there is no radial drift. So dust is always mixed with gas, almost. But on the other hand, in the right panel, you can see that dust particles can grow larger and they drift radially. And eventually, the dust surface density decreases by orders of magnitude with time. So based on these simulation, okay, And based on this simulation, we perform the imaging simulation and the dust radiative transfer simulation to estimate the temperature structure and compare with observation. Okay, so this is a comparison with the ALMA dust continuum observation. And we showed two models. One is the model with the temperature determined by stellar irradiation. And the other one is the temperature determined by accretion heating and external heating. So this is our model. And for each model, for each temperature model, we show two models with different fragmentation velocity. All right? And if we look at the left model with a temperature determined by stellar irradiation, and this figure shows the dust continuum intensity as a function of the radial distance, and the solid line shows the observed intensity, and the dotted line shows the model intensity, right? And we have two observations at two wavelengths. And you can see that the model intensity is much lower than the observed intensity, regardless of the fragmentation velocity, right? And the point is that we already assume gravitationally unstable disk, meaning that we cannot increase the surface density anymore. So this is a maximum massive disk in our model, right? But still, the model emission is lower than the observed value. So in this model, we cannot reproduce the observation. But if we look at our temperature model and with very low fragmentation velocity, our model reasonably reproduces the observed intensity profile as shown in this figure. But if the dust is sticky, I mean the fragmentation velocity of 10 meters per second, then the model intensity is much lower than the observed value. So based on this comparison, we can say that the dust should be very fragile, and our temperature structure is more consistent with the typical temperature structure determined by the stellar irradiation. Okay, so this is the first findings of our study. And now we compare our model with the millimeter polarization observations. And for this disk, we have two polarimetric observations. One is the 0.9 millimeter, and the other one is a 1.3 millimeter. And at both wavelengths, we detect the scattering induced polarization, where the polarization vector is parallel to the disk minor axis. And the polarization fraction is roughly 1%, which is consistent with the scattering polarization. And this is a comparison with comparison of observation and our model. These two figures show the observed polarization image at 1.3 millimeter and 0.9 millimeter. And these three columns shows our model with different fragmentation velocity and different dust porosity or dust filling factor. So dust filling factor of 0.2 means that the porosity of 0.8. So this is moderately porous dust particle. But filling factor of unity corresponds to the compact dust particle. And you can see that if dust is moderately porous and very fragile, then the model intensity is very consistent with the observed value, right? But if we look at the fragmentation velocity of 10 meters per second, or the very compact dust particle, then the model polarized intensity is much fainter. So again, based on the polarimetric observation, fragile dust is preferred. And also, the moderate porosity is preferred. So the conclusion from this comparison is that moderately porous fragile dust explains the observed millimeter polarization. So I want to emphasize, based on in this comparison, we do not do any fine tuning of the model. We just change the porosity and the fragmentation velocity. These are only the free parameter. The other parameter is completely determined by observation or theories. So I'm very surprised that without any fine tuning, we can reproduce the Stokes emission and polarize the emission very well.
So, excuse me, so you consider the compact or porous dust in the polarization equation. So do you consider the porous dust in the dust growth calculation?
Yes, yes. So I do not, yeah, that's a very good point. I do not mention that, but in this simulation, we also change, we also change the porosity for each simulation. So there are two simulations. One is fully compact dust particle, and the other one is a porous dust particle. But the porosity is fixed in the simulation. So dust part, for example, if we assume the porosity of 0.2, then every dust particle has a porosity of 0.2.
You mean every size?
Yes, yes, every size and every entire region of the disk. And in reality, probably the small grain has higher porosity, and the larger particle has a lower porosity. But basically, I expect that ALMA observation traces a large dust particle. And I think the porosity of the large particle is our preferred porosity is for the large dust particle, basically, because ALMA observation traces are large grains. Okay, so finally, I want to compare our model with the infrared scattered light. So this observation basically traces small grains. And before going to the comparison, I'd like to briefly mention that what kind of image we compare. So this is the original polarized emission image at 1.6 micron. And you can see that very beautiful flared disk structure. And there's a dark line at the midplane, right? And if we multiply the intensity by the square of the radial distance to compensate for the stellar flux attenuation to trace the surface density, surface structure of the disk. So this is basically because this aims to see the surface structure, because the stellar flux is inversely proportional to the square of the distance. To compensate for this decline of the stellar flux, we multiply by the square of the distance. And you can see that the scaled polarized emission shows the dark inner hole, ranging, extending to the, let's say, 100 AU. And outer that, there is a very beautiful flared disk structure. And this is a comparison of the observation in the left, and the right three panels shows our model with our fragile dust model. And these two panels shows the model with power law temperature profile expected from the stellar radiation. And you can clearly see that our model is roughly consistent with the observed image. But if we assume the typical power law temperature profiles, by the way, these two power law temperature is slightly different each other, but overall behavior is very similar. So you can see that if we assume the power law temperature expected from the stellar radiation, we cannot reproduce this inner hole-like structure and very beautiful flared disk surface. But if we assume the accretion heating and external radiation, this observed disk surface structure is naturally explained. Right? Okay, so basically our theoretical model can explain these observations very well without any fine tuning. But only assumption here is that temperature structure, right? So the question is that this temperature model is consistent with the dust distribution, right? Because the disk temperature structure is determined by the distribution of small grains, right? So to investigate that, we perform the iterative Monte Carlo radiative transfer simulation based on the dust evolution simulation. And we do that what we do is that we input the disk structure obtained from the dust evolution simulation and perform the radiative transfer simulation and obtain the temperature structure. But this temperature structure depends on the input disk structure, which depends on the temperature. So we iterate this step until the disk structure is converged into the one solution. And we implement the effect of the accretion heating and the external heating. And this is a result. This left panel shows the mid-plane temperature as a function of the radial distance. And this black line shows our assumed temperature structure. And this red solid line, shows the model with the fragmentation velocity of 0.3 meter per second. And the other three lines correspond to the different fragmentation velocity. And basically, we can see that if the fragmentation velocity is 0.3 meter per second, the temperature structure is also consistent with the assumed temperature structure. So meaning that if the fragmentation velocity is really 0.3 meter per second, we do not need to assume temperature structure. We can self-consistently obtain the disk structure without any ad hoc assumption. But if dust particle fragmentation velocity is higher, then disk temperature is basically lower than the assumed temperature structure. So this means that even the temperature structure, which is very uncertain from the observation, is also prefers a fragile dust particle. And the right figure shows the two-dimensional temperature structure for the very fragile dust particle with fragmentation velocity of 0.3 meter per second, and the bottom panel shows the fragmentation velocity of 10 meter per second. This is very complicated figure, and I don't want to explain the detail, but what I like in this figure is that, so this is very complicated figure, but this background color map shows the temperature structure obtained from our radiative transfer simulation. And this dotted blue dot shows the observed CO brightness temperature obtained from the ALMA observation. And this dot also has a color scale corresponding to this background color temperature map. And you can see that, for example, if we look at the bottom panel, the brightness observed CO brightness temperature is lower than the temperature structure obtained from our simulation, right? You can see, for example, this one, the brightness temperature is something like the 20 Kelvin or something like that. But the simulated temperature is something like the 40 Kelvin or something like that, right? So basically, the observed brightness temperature is inconsistent with our simulation. But if we look at the fragile dust scenario, the CO brightness temperature is also consistent with the temperature structure. That is something surprised, because our model is based on the dust distribution, and we do not aim to reproduce the gas brightness temperature. But still, we can obtain the very good agreement with the observed CO brightness temperature. Okay, so there I want to briefly mention about the implications from the fragile moderately porous dust scenario for the planet formation. Actually, if we, in this disk, there is a potential protoplanet candidate at 100 AU. So if we look at the intensity profile as a function of the radial distance, you can see that there is some small gap-like structure at 100 AU. So this gap can be generated by the embedded planet with a mass of the roughly Jupiter mass. And also the kinematic observation of the 12CO221 line emission indicate the presence of the giant planet at this location. So the basic question is that if dust is very fragile, can giant planet form at 100 AU within the age of this disk, which is roughly 1 million years? So we calculate the growth time scale of the planet at 100 as a function of the radial distance based on the pebble accretion scenario, where the planetary core can grow rapidly by capturing the drifting pebbles. So this is one of the most common scenario for the planet formation in this disk. And we showed the growth time scale of planet for different fragmentation velocity. And this horizontal line shows the typical age of the IM Lup disk. And you can see that if dust particle is very sticky with fragmentation velocity of 10 meters per second, the planet growth time scale is roughly order of the 1 million year at 100 AU, meaning that if dust is sticky, maybe giant planet can form at 100 AU within the age of the IM Lup disk. However, if dust is fragile, the growth time scale of planet is much longer than the age of the IM Lup disk. So meaning that if giant planet is present at 100 AU, this giant planet should be formed by the other pathways, such kind of the due to the direct collapse of the spiral arm induced by the gravitational instability, or something like that. And the implication is for the porosity is that basically in the disk, pairwise collision of dust particle result in the very extremely porous dust aggregate with a filling factor of the much less than 0.1, which is unlikely to explain the observed polarization degree in this disk. However, moderate porosity can be achieved by the hierarchical growth of dust particle, where the void in the large aggregate can be is filled by the very small grains, and eventually the porosity is decreases by such kind of the filling up of large void by the small grains. And actually, if we look at the solar system small bodies, the cometary dust is commonly detected to be the moderately porous, with a porosity of the 0.7 or 0.8, something like that. So basically, our result is consistent with the porosity inferred from the solar system small bodies. So I want to emphasize, so I'm not sure that this is a very general behavior of dust evolution in disks. I only performed the modeling for only this target, but so I hope this is a kind of general consensus for the dust evolution. So this is a summary of my talk. Thank you so much.
Okay, so any question? Okay. In your model, what's the maximum grain size?
Sorry?
Maximum grain size in your model?
In my model? So, sorry. So basically, for example, if we look at the 100 AU, then dust size should be, let's say, 100 micron. But if we go to the 10 AU, then dust size should be few millimeter or something like that. And if we look at the 1 AU, then it can be order of centimeter.
For the temperature, in a region in your model, it's heated by the accretion.
Yes.
And this accretion input is from the accretion estimated with the observation,
Yes.
10 to the minus 8.
Yes.
So, does it impact your model if the accretion to which radius the accretion flow stopped? Because in the observation, we also know there is probably a planet at about 100 AU.
Mm-hmm.
while you also have an accretion rate of 10 to the minus 8, but we don't know where is the radius where the accretion flow.
I see.
Right? So does that impact your model?
Okay. So please let me rephrase your question. So if the mass accretion rate depends on the radial distance, then
we know the accretion is the material is falling onto the system, but we don't know at which radius this flow stop or enter to the system.
Yeah.
That's my question.
Okay.
Does that impact your model?
Yes. Okay. That's a very good point. So basically, in terms of the surface density first, so surface density, alpha value depends on the mass accretion rate, proportional to the mass accretion rate. So if the accretion rate is 10 times higher, then alpha value is 10 times higher, right? So I think the higher mass accretion rate is acceptable. And if, for example, accretion rate is 10 times higher, then alpha value is also higher, so that the fragmentation velocity can be also higher by a factor of 3, I think. Yeah, because the point is that the important thing is the physical size of dust particle. This is inversely proportional to the alpha value and proportional to the square of the fragmentation velocity. And if accretion rate is 10 times higher, then alpha value is also 10 times higher. So to achieve the same dust size with my simulation, we need to increase the fragmentation velocity by a factor of 3, right? So
I think my question is then what if the alpha value is radius dependence?
Right.
So then that also implies your fragmentation velocity would be also radius dependent.
yes, yeah.
Therefore, the constraint on the grain size and so on.
Right. Yes. So basically, at least, yeah, that's a very good point. So if we look at the high resolution simulation, there is some local variation in the intensity. So we expect the accretion rate can also vary with radial distance. But how to say, first order discussion with lower resolution observation, I think the constant mass accretion rate is a reasonable assumption.
That M dot, I think, was measured by like black gamma or kind of signal. This is looking at the accretion shock at the stellar surface. So the accretion must be hitting to the star, actually, not stopping somewhere in the disk. I don't think so.
10 to the minus 8 is
Okay, so let me clarify that the accretion rate of 10 to the minus 8 solar mass per year is accretion rate onto the central star. Okay. But point is that the accretion rate at the very inner region is 10 to the minus 8 solar mass per year. But as you say, for example, if we look at the outer region, the mass accretion rate can be different from the inner region. So that's a point.
Okay. Any more questions? Yeah. Okay.
So in introduction, you mentioned you want to know the turbulent strength.
Mm-hmm.
So can you estimate the turbulent strength in your?
Yes. So that's a good point. So the point is that the dust size depends on the turbulence strength and the fragmentation velocity. And both parameters is very uncertain. But so in my model, based on the observed accretion rate and the dynamical mass of the central star, we can estimate the accretion stress alpha with this equation. So, and this value is something like the 10 to minus 3 at the outer region, and it can be 10 to minus 5 or 10 to minus 4 at the very inner region of the disk. So that alpha value is not a free parameter in this model. We can estimate the alpha parameter based on the observed parameters. So this is kind of the important point, because in the typical other studies, there is a degeneracy between the alpha value and the fragmentation velocity. But in our model, the alpha value is constrained from the observations, and we can estimate the fragmentation velocity independent of the alpha value.
But in your model, you assume the target mechanism is gravitational instability,
Yes.
right?
Yes.
But for the inner region, the temperature is very high.
Yeah.
So MRI might be active.
Yes. So for example, if we look at the within 1 AU, the temperature can be order of the 1000 Kelvin. So the within 1 AU, MRI can be activated. Yeah.
But you focus on the outer region.
Yeah, beyond 1 AU. Yeah.
So basically, here that you mentioned that the turbulence velocity and gas density is kind of important
Yes.
parameter.
Yeah.
Only think the other way, so that if we observers observe the molecular gas, you can derive gas surface density and turbulence directly. Depends on where the molecular gas locates.
Yeah.
Then you model can predict what whatever molecular gas depends on the location that
Right.
if it is mid-plane, this kind of surface density and this kind of turbulence velocity should be observed, or you can predict that.
Right. Yeah, that is something in the very. So I think the future work is something like that. So we are interested in the gas molecule observation, this chemistry, and actually there is some observation of the turbulence broadening of the gas molecule observation at the very outer region of this disk. And I think such kind of observation basically traces the surface layer of the disk, so which is different from the midplane. But the observed value is something like here, so the order of 10 to minus 2, or something like here. So basically, it's not so different, because in this disk, we expect that the turbulence strength at the surface is stronger than the disk midplane. So basically, the observed value is not inconsistent with our model. And the gas surface density, we have there is some observation of the CO, but if we estimate the gas surface density from the CO, we have to convert the CO mass to the 82 mass, and there is a large uncertainty, so we cannot precisely estimate the gas surface density from the CO line observation.
I have a question about the number of tumor Q value you assume. So you assume a critical value for tumor Q parameter. So does your result change if you change the number?
Okay, yes, that's a good point. Yeah. So basically, roughly speaking, our model basically shows the lower intensity compared to the observation. So we need higher surface density to explain the observed value. So basically, for example, if we look at this equation, we prefer lower Q value. And so for example, we already assume very low Q value, and I think it is unlikely that the tumor Q parameter is something like 0.1. I think it's very unlikely, and so basically this is a kind of, how to say, most optimistic model to explain the very bright emission with the IM Lup disk.
All right. Okay. So he's going to still stay actually this week and next week. Although next week he's mostly at the workshop, ARPA workshop, but he's staying at room 1108. So if you want to discuss with him more, then just visit his office or just talk to wherever he is. But anyway, let's thank again.
Thank you.